तो मैं कहाँ पहुँचा था, आई डोंट नो। ठीक है, मैंने शायद अच्छा मैंने ये किया था प्रूव, इंटीग्रल gn power p is strictly less than norm of 1 minute. Strictly less than norm of 1 plus no, so it was norm of f1. I think norm of f1 plus 1, it's pth norm, okay, plus 1 power p, ये हमने किया था। अब फिर मैंने इसमें लिमिट अप्लाई किया था, लिमिट एन अप्रोच टू इन्फिनिटी इंटीग्रल gn power p is less than or equal to norm f1, it's pth norm, or you can say LP norm, which is a finite thing. So we can apply the Levy theorem on gn. Therefore we can apply Levy's theorem on this sequence gn. We can apply Levy's theorem on gn. So what's Levy's theorem? We know that Levy's theorem क्या है? What's Levy's theorem?
पता नहीं।
क्या कह रहे हो आप लोग, पता नहीं? बताइए ना, लेविस थ्योरम का स्टेटमेंट क्या है? नो, तो लेविस थ्योरम का स्टेटमेंट ये है, अगर आपके पास होगी इंक्रीजिंग सीक्वेंस इंटीग्रेबल फंक्शंस की, क्या होगी? इंक्रीजिंग सीक्वेंस होगी इंटीग्रेबल फंक्शंस की, और ये इसकी पहली प्रॉपर्टी है। सेकंड प्रॉपर्टी ये है कि अगर इसका जो लिमिट एन अप्रोच टू इन्फिनिटी इंटीग्रल एफ एन इफ इट्स फाइनाइट, ये दो प्रॉपर्टीज होनी चाहिए इस सीक्वेंस की। इट्स अ सीक्वेंस ऑफ इंटीग्रल फंक्शंस। फर्स्ट प्रॉपर्टी, it's monotonic increasing. Second property, limit of the integral of fn is finite. Then Levy's theorem states that there exists a function f which is integrable such that fn increases to f and the limit of the integral of fn is equal to integral of limit of fn. That's our Levy's theorem. So it speaks that given a sequence of integral functions having the following properties, so that's first property, that sequence is monotonic increasing. Second property, limit of the integral of that sequence is finite. Then this guarantees gives the guarantee that there exists a function f which is integrable such that this fn, it converges to f and limit of integral of fn is equal to integral of limit of fn. तो इसका यूज हम gn पर करेंगे, क्योंकि gn की ये प्रॉपर्टी है। gn एक तो मोनोटोनिक इंक्रीजिंग है, और सेकंड आपने प्रूव किया लिमिट ऑफ द इंटीग्रल ऑफ gn पावर p इज फाइनाइट फॉर ईच p. So this Levy's theorem, we can apply the Levy's theorem on gn. So there exists a function, there is some function, you can see some function g belongs to LP mu such that this 0 which is less or equal to g, and it is non-negative, and it is also increasing and increases to g. So this is not actually norm convergence. This is the point-wise convergence. This is point-wise convergence. So there is a difference between point-wise convergence and norm convergence. So this limit is almost everywhere. Now let's take this difference mod of fn plus k minus fn. Let's take this difference, and you can see this difference is equal to, so I'm not going to explain it, you can easily verify it. If you expand this sum, you'll see this is equal to that difference. I runs from n plus 1 to n plus k fi minus fi minus 1. So you can easily verify this one इसके बराबर है. Then this is let's apply the triangular inequality of mod. Summation I runs from n plus 1 to n plus k mod of fi minus 1, fi minus 1, and this one, if you see this sum, it's equal to gn plus k minus gn plus k minus gn, or you can also put mod here, because this gn plus k is greater or equal to gn, so you can also put mod. So we have this mod of fn plus k minus fn is less or equal to gn plus k minus gn, and this gn plus k, it converges to gnx point-wise. So that means this is actually it's like a Cauchy sequence in R if we take the convergence point-wise. So which means that this sequence is also, which implies that this implies fnx, okay, fnx is or I will use this terminology. I don't know whether this is there or not, but let me use this. This implies this fn is a Cauchy sequence almost everywhere. Fn is a Cauchy sequence, point-wise Cauchy sequence, I can say, as gn is a point-wise Cauchy sequence. Point-wise Cauchy sequence almost everywhere. So अब मैंने point-wise Cauchy sequence की use किया. I don't know, this is not in the literature, but point-wise का मतलब क्या है? Point-wise Cauchy sequence means that this one. एक तो है कि Cauchy sequence in norm. Norm means this. Norm of fn minus fm is less than epsilon, like that, for all nm greater or equal to, say, certain integer n naught. But point-wise means this. Mod of fnx minus fmx is less than epsilon for nm greater. This is the point-wise, and almost everywhere means this is not true for each x in the space. It's true for each x except on a set having major 0. So that's why I have used this. fn is a point-wise Cauchy sequence in that sense. आप इसको समझ लेना कि कहने का मतलब क्या है. fn is a point-wise. Point-wise means this. It's mod actually, not norm. Point-wise and point-wise Cauchy. almost everywhere means it's not true for each x because Jn is not Cauchy, point wise Cauchy for each x. आपको ये मेरी बात समझ आ रही है? मैंने क्या लिखा है यहाँ पर? So this is the point-wise Cauchy sequence, and in R actually, so that means, this means, because R is a complete matrix, R is a complete, you can see it's R is a Banach space also, or R is a complete matrix space. So it follows that there, it implies that the sequence Fn converges point-wise. Converges point-wise to some function f, to some function f, to some function f. So almost everywhere. So that is Fnx converges to fx almost everywhere. Almost everywhere. Now again we have this mod of fn, which is equal to mod of f1 plus summation I runs from 2 to n, then it's fi minus fi minus 1. Okay, so you can see this. Okay, this is simple. You just expand this sum and some terms will cancel out, and you'll finally see that this whole the term under the modulus on the right hand side, it will be equal to fn. Okay, this is very simple. And this one, it's lesser equal to mod of f1 plus mod of this, mod of f1 plus summation I runs from 2 to n mod of fi minus fi minus 1, and that one, that mod, that sum of mods, it's equal to gn. It's equal to gn. ये gn के बराबर है, and gn is lesser equal to g because gn is increasing sequence and it increases to g. So that means this gn must be lesser equal to g point wise. It's lesser equal to g almost everywhere. It's lesser equal to g almost everywhere. So it follows that अब देखिए mod of fn is lesser equal to g आ गया now. So this means mod of fn is lesser equal to g almost everywhere for all n greater or equal to 1. So this means its limit, which is f, or you can say mod f, is lesser equal to g for all n greater or equal to 1. So that means this minus g lesser equal to f, lesser equal to g. Sorry, it's not here for all n. So this f, it lies between two integrable functions, and it's a measurable function because it is the limit of the sequence of measurable functions. So which implies that f is in LP mu. F belongs to LP mu. So we have the following: fnx converges to fx pointwise almost everywhere, and this f, it belongs to LP mu. But still this LP is not complete because we need to show that the norm convergence. Actually we have to show that norm of fn minus f should approach to 0. So how do we do that? We have this one, f minus fn, this mod, it's lesser equal to mod of f plus mod of fn. Okay, we have this f minus f, it's but mod of f is lesser equal to g, mod of fn is lesser equal to, it's lesser equal to twice g. So we can apply the Lebesgue dominated convergence theorem on this sequence. So we can apply because this sequence f minus fn, it is dominated by this 2g, which is integrable. We can apply the Lebesgue dominated convergence theorem on this sequence f minus fn. f minus, इस sequence पर हम apply कर सकते हैं Lebesgue dominated convergence तो इसकी इसमें इसकी क्या क्या प्रॉपर्टीज है इस सीक्वेंस की? अगर आप इसकी प्रॉपर्टीज देखना चाहोगे, वी हैव दिस लिमिट एन अप्रोच टू इन्फिनिटी mod of f minus fn, the point-wise limit, it's equal to 0 almost everywhere. So its limit function is 0, and this implies the limit of the integral must be equal to 0. So this implies that limit n approach to infinity integral of mod of f minus fn power p, it's equal to the integral of the limit that you know, because by Lebesgue dominated convergence theorem, so limit of the integral is equal to the integral of limit f minus fn power p, but this limit is equal to 0, it's equal to 0. But on this side it's actually the norm, ना, ये असल में नॉर्म है, अगर आप इसको देखोगे, दिस नॉर्म. So this implies, this norm power p, this implies limit and approach to infinity norm of f minus fn p whole power p is equal to 0. So which implies limit and approach to infinity norm of fn minus f is pth norm, it's equal to 0. So that means this fn converges to f in LP norm. So that proves LP is, hence LP is complete. You can say Banach space, hence LP mu is a Banach space. Is a Banach space. So that was Riesz Fischer theorem. इसमें अगर कोई क्वेश्चन है तो वो पूछिए आप. Any question in this lecture?
सर वो माइनस जी लेस और इक्वल टू एफ लेस और इक्वल टू जी, उससे इम्प्लाई ऐसे होगा कि एफ एलपी में.
ओके, हाँ ये क्वेश्चन आपने सही किया, क्योंकि इसको मैंने पूरा एक्सप्लेन भी नहीं किया है. अगर आपके पास ये है ना, mod of f is less or equal to g, ओके है ना ये आपके पास. This implies mod of f power p is less or equal to g power p. So which implies minus g power p is less or equal to f power p, which is less or equal to g power p. So that means this f power p is measurable function, and g power p is integrable, because integral of g power p it exists, है ना, इसका mod का इंटीग्रल वो x2 हो रहा है. So that means f power p का जो इंटीग्रल होगा ना mod, this implies integral of mod of f power p exists. It's finite thing. It's a finite thing. Because g is in LP mu, g LP mu में है. तो पहले p पावर आप लीजिए, फिर आप p पावर फंक्शन जो है ना उस पर आप वो रिजल्ट अप्लाई कीजिए, not on the simple function f or g. pth पावर एक्चुअली आप, क्योंकि आपको pth पावर इंटीग्रेबल चाहिए. आपको मेरी बात समझ आ रही है?
यस सर.
ओके, और कोई क्वेश्चन? So should we stop? Shall we stop our lecture? Yes. हाँ
सर इतना ही पढ़ लेंगे.
ओके.